And yeah, it's kind of a dance between the eddies in the atmosphere and the eddies in the ocean. Um, Definitely not drunk when I make this. Um, all right. So the relationship between tropical cyclones and the upper ocean is a two-way interaction, right? It is. I think it's relatively well known that the ocean affect tropical cyclones by providing energy to fuel the storm, intensification, development, and everything. But at the same time, tropical cyclones actually provide mechanical energy to the ocean through their strong wind forcing. And it is this part of the interaction, the TC wind force on the ocean, is one of the key processes that tropical cyclones can affect our climate state. And this is what my talk will be focused on, and I will now explain how this works. So the basic mechanism is that when the tropical cyclone moves over the ocean surface, it will cause this very strong ocean vertical mixing because of the strong TC winds. And the mixing process would bring up the cold water from the ocean subsurface to the surface, and at the same time, pump the surface warm water down into the ocean interior. So as a result, if you observe from the ocean surface, you will normally see a cold temperature anomaly. We often call it as a SST cold wave along the tropical cyclone track. And if you look at the subsurface temperature profile, which is shown in this little panel here, the black shows the ocean vertical temperature distribution before a tropical cyclone passes, and the gray is after. You see, after the wind forcing, we'll have a deepening of the ocean mixed layer. And if you plot the difference between these two vertical temperature profile, you will get a cold temperature anomaly at the near surface and a warm temperature anomaly underneath. So after have temperature redistribution after about days to weeks, or maybe even a month, your near surface cold temperature anomaly will be eventually restored to pre-storm conditions, mainly through the heat flux adjustment with the atmosphere. But the warm temperature anomaly, if it's pumped down deep enough to the ocean thermocline, where it is well protected from the surface processes, it can stay there for a much longer time. If they can survive the winter mixer deepening, they can be there on interannual timescales or even on decadal timescales. So this is intriguing. We have this process, through this process, we have from ocean vertical mixing induced by tropical cyclones, eventually come to a net heat gain into the ocean. So tropical cyclones put heat into the ocean interior. All right. So naturally, our question is, how much heat? What does the heat do? Where does it go? And how does it come back to the atmosphere and affect the climate? All right. And these are the questions that I strive to answer in my research. So this idea was first suggested by Kerry Emanuel in the early 2000s. He found that tropical cyclones through this process may affect the ocean heat content and heat transport, which contribute to a substantial fraction of the polar heat transport in the Pacific Ocean. And then a lot of studies, including observational and modeling, followed the study of Kerry Emanuel and had a lot of interesting findings. But these studies are all limited in different ways because, as you can imagine, this is a very hard topic. We're talking about the impact of weather on climate. First, observation is sparse. We don't have a lot of ocean observation under a moving storm, right? And if you want to use models, you will first have to think about how to represent weather. It should be high resolution. And then you'll have to understand it in a climate setting. So it'll have to be integrated for a long time. And ideally in a global climate model, coupled, if you can afford it, maybe ensembles. So it can get really, really expensive. And you also need to think about how to isolate the signal of tropical cyclones, right? So these are the hard questions that we need to tackle. And I think relevant to our MIP and a lot of discussions on Monday and Tuesday about high resolution climate modeling. Because we don't know TC's role in the high resolution storm permitting climate models. If they do have an impact on the global climate, this effect are automatically incorporated into the model itself, right? The model produce their own tropical cyclones, and their own tropical cyclones affect their own climate. We wouldn't know how much uncertainty is there associated with this process, and whether this is uncertainty is reflected in our model's projected future climate. Yes, and then another question is that we also need to understand this process in the fully coupled frameworks. As I said, this is a tightly coupled process. We want to know, I put this here because a lot of studies, including myself, are all about ocean-only simulations where you use TC winds to force the ocean. But we ultimately want to know if we put heat into the ocean, ultimately, how does it come back to the atmosphere and affect the whole coupled system? So ideally, we want to study it in the coupled framework. So these are all the challenges that we're facing to try to understand this question. So last year, maybe 2 years ago, maybe it's longer than I remembered, we designed an experiment to try to understand this process, which I will show in a minute. But before that, you may be asking, okay, now you're talking about tropical cyclones and the climate models. Can the climate models can even capture this process? So what I'm going to show you is then visualization years ago about TC's impact on the ocean. This is a 10th of a degree eddy resolving ocean. This is an ocean-only simulation where we put in tropical cyclone winds and then see how the ocean responds. And this is looking at a tropical ocean at the tilted angles. You will see temperature responses both at the surface and in the subsurface. You will see. Sorry, I explain this before I play it. The cold temperature anomaly will be in blue, and the warm temperature anomaly would be in yellow. And then these moving black dots are tropical cyclone locations. They're just moving, and you will see cold temperature on the surface, warm temperature underneath. That is all captured by this global eddy model. And you will see a TC in the Western Pacific actually triggered this rapidly eastward propagating equatorial Kelvin wave and carried with it the heat anomaly that the TC pumped into the ocean thermocline. So you can see tropical cyclones, it's kind of provide a pathway of rapidly moving heat from the western equatorial Pacific into the eastern equatorial Pacific. So this visualization is only a year and a half. And then at the end of the simulation, you can see the foot the cyclones all over the place. So this is just to show you TC's impact can be captured in these climate models. So next, I'm going to talk about how we designed the experiment. So we use two different versions of the CESM model, which is a community Earth system model developed at NSF NCAR. So we're going to use two versions. One is a high resolution version, a TC per meeting with 1/4 degree atmosphere coupled to a 1 degree ocean. This one is mainly used to provide tropical cyclone wind pulsing. Oh, wait, that's not good. Should I do something? Or did I do something wrong? Okay, so it's the projection. Did I? Ask questions.
Yes, questions now, please. We're taking a quick break. Just kidding.
Doesn't cut into my time, just okay.
We'll try. Do you want to ask? We'll try.
So I was going to ask the movie. So how did you isolate that those anomalies were due to TCs rather than something else?
So we have two sets of simulations. We have a simulation that without TC and another with TC.
Okay.
That's the beauty of using ocean-only model, so you can determine what goes into the ocean.
Okay.
Yes.
Okay. Right. Thanks.
to decide.
Yes, looks fantastic, and the animations very brings home the message indeed. So yeah, we saw half a year, and the thermocline changes stay there indeed. But yet I don't see circulation happening. Is the circulation of the ocean realistic in the?
Realistic?
Yeah.
I hope so. It's a CSM ocean top model.
Yeah, yeah.
Yeah.
But yeah, so and also the surface stays blue for a long time.
Yeah,
Uh,
because you always have tropical cyclones happening during this time.
Ah.
But if you look at the composite response, which I will show, you will see indeed after 30 days after, we will have the surface restored. Yeah, and then warm.
Yeah.
Yes. It's not too obvious on this animation.
Yeah, just before you go on, they are trying to find the technician.
Okay.
Does it move to?
Oh, we have plenty of questions.
Yeah. So can I?
Yeah, go ahead.
Okay. Considering that most of those cyclones were in the northern hemisphere, and we know that winter mixing can actually let this heat escape. How come that you started simulations in January and ending in December? Because it would have been interesting to see the whole winter season, what effect it would have had on this warming.
Yeah, actually, our simulations are longer, but this is part of the study that we use for visualization. And you can imagine this is eddy resolving, so it's expensive at the time. But you're right, we find that the heat actually survived the winter mixed layer deepening. A very recent study last year, it's an observational study, find that the heat can go down to below 300 meters and can persist, beyond the winter time. Yes.
Yeah, I'll echo that simulation or the video is like super cool. I was curious, so the way you said the way you isolated that is you run like one simulation without the TC wind signature and then one with, and then it seems like you just diff the two. Have you tried putting like noise, like I'd be interested, like I don't know how nonlinear like that Kelvin wave response is. Like if you put some sort of noise in the simulation, do you get the same behavior? Like I assume those were only two simulations, right? Not like an ensemble. Oh. Yeah, because once the signal goes into the ocean, you would expect that the ocean will just do what it wants to do. So you could get kind of this either amplified, like, so yeah, that especially that response across the Pacific was like really stark. I'd be curious to see how robust that was in like multiple simulations, but
Equatorial Kelvin waves. So I think, yeah, it is a good idea. Best results.
Very cool. We'll do one more question.
Yeah, similar kind of question and follow up was that it looked to me, well, I mean, who knows, but I was thinking of westerly wind bursts that trigger these waves, but often are associated with twin TCs, where you have a tropical cyclone in both hemispheres and gives you a stronger westerly wind burst in that region. So, but this was just a single event, right? It wasn't too. Okay.
I believe this is a single event, but I think it's actually you will be surprised. I think study says 60% of tropical cyclones are associated with westerly wind bursts. So there are actually a lot of overlaps. Yeah, but in this case, it was just one cyclone. Maybe it's strong enough, and it was very early season.
Yeah.
So maybe that's why it's able to trigger this wave reaction.
Great.
Yeah.
All right, take it away, Wei.
I was talking about experiment design using two versions of CSM. The high resolution to provide the TC windfalls in the low resolution. Below is a 1 degree model, 1 degree atmosphere coupled to 1 degree ocean. So we found that in CSM 1 degree model, you have maybe 8 to 14 TCs per year, but they're all below category 1. So we're going to regard this model as not having strong TCs. All right, so we have kind of a control without strong TCs, and we're going to add well, not realistic, but model simulated tropical cyclone winds into this 1 degree model. So this is to show 30 years of tracks in the observation compared to the 1/4 of a degree CESM. You have climatology, just spatial distribution and number relatively realistically compared to the observations. And then what we did next is that we track all these, and then at each time step, it's a 6-hour interval, I believe. We take a snapshot. It should be moving, but it's not. We take snapshots of the TC winds, surface winds, within a 20 by 20 degree domain box. And then we collect all these TCs into a TC wind forcing repository. And all these TCs are still preserve their timing and location and every information we collected. And then we add these TC winds into the 1 degree couplet model on the fly as the model runs. So if you are familiar with CSM, we added into the coupler component. We did it in a way so that still, again, these TC winds are added to the model, preserving their initial time and location. So the ocean component in the 1 degree model can see the tropical cyclone wind forcing exactly as the ocean component in the high resolution sees the wind forcing. So we kind of use this way to mimic the behavior in the high resolution model. But for this, we can run hundreds of years. So yeah, run this model with TC forcing for 100 years. This is just to validate, this is the surface wind stress detected after TC winds are added, just to show you this, and the winds are successfully added. And we also have a control simulation, another 100 years, that we can isolate the impact of TCs by comparing the, this stands for low res, 1 degree is not so low res TC and the low res control, which does not have TCs. So that is the method. I hope I explained it well. Okay, so that was the whole setup, and we're gonna look at what we found in this model experiment. So first of all, we wanna look at the processes on individual storms. So we did a composite analysis. So by that, at each individual day and composite them together. So the top 2 panels are the time series of the SST anomalies. These are the difference between the TC run and the control run. And these anomalies, I believe, are averaged over 60 degree domain box surrounding the TC center. And x-axis is time. So at day 0, you have tropical cyclone hitting a specific location. So you have a TC coming, hit this location on day 0, and it's going. But we keep monitor the location and how the SST in this region changes. We find that after TC hits the location, you have a cooling that maximizes on day 3. This is for all tropical cyclones. These are for intense tropical cyclones only. And this response is consistent with ship observations and satellite observations. So we know that even at 1 degree, the model can kind of capture this, these changes in the sea surface temperature following the TCs. And the lower 2 panels are showing the ocean temperature structure changes under the TC. This axis is now distance, in the middle is the TC center, and the y-axis is the depth in the ocean. You will see right under the TCs, you have this cold column that is mainly induced by vertical mixing and also ocean upwelling. And then around just below the ocean mix layer, you have some warm temperature anomalies that is due to mixing, but they're all mostly on the peripheral because the upwelling signal is too strong. And then if you want to take a look at how this structure evolve, we kind of take an average of this domain and plot a time series. So now the x-axis is days, y-axis is your depth. So when you see that, right, so day 0 would be like this, and then you average this, you get this. You have a cold temperature anomaly at the near surface and a warm underneath. And as time goes by, around 25:30, you can see the surface temperature, a cold temperature anomaly kind of dissipates, and the warmer temperature is still there to stay. This kind of answers Paulo's question before, like how the SST at the surface cold temperature anomaly changes. So from this, we see that in the process level, in these models, can capture the TC region interaction even at 1 degree, okay? So now we're gonna look at the integrated response. This is, first of all, the ocean heat content changes. We just, look at the red lines, there's only relevant line. X-axis is the time. This is 100 years of simulation. We see that the ocean heat content integrated over the top 1,000 meter ocean increases. in the TC run compared to the control run. And we find that the magnitude increase about 0.03 petawatts per year, which is a substantial amount. And then if we want to take a look at where does this heat go, we look at the pattern of the ocean heat content anomaly. This is the climatology. This is the difference between the TC run and the control run. We see the heat mainly concentrated in the eastern equatorial Pacific, in the subtropics, and also in the mid latitudes. This reminds us of the circulation where the subtropical cells would transport the heat from the equator to the higher latitude, which I will show later. Yes, and then more relevant is maybe the sea surface temperature anomalies we see from this model. So again, this is the difference between TC run and control run. We see the temperature patterns induced by the tropical cyclone wind forcing. It kind of have some resemblance with the ocean heat content changes. Again, we have some warming in the eastern equatorial Pacific and some warming in the subtropics and something in the area of alluvion low and in the North Pacific Ocean. And then we also find changes in surface heat fluxes. Here, the warm colors are showing heat going into the ocean. The cold is coming out of the ocean. You will see the cold areas would have heat going into the ocean, while the warm areas would have heat going out, which shows that this heat are controlled by the ocean rather than the atmosphere. And lastly, we also look at precipitation. So tropical cyclones can affect your global precipitation patterns in our simulation. You kind of have a drying in the Western Pacific and the Indian Ocean, Southern Indian Ocean, and you have some increased precipitation in Eastern Equatorial Pacific. So from here, we show tropical cyclones in this setting, model setting, can affect your climate mean state. I should probably mention these are the average over the last 30 years of our simulation. All right, this is a 100-year simulation. These are showing the anomalies in the last 30 years. So their contributions are non-trivial. We also then take a look at the ocean subsurface temperature changes. This is the zonal temperature average, I think maybe 5 degree to 5 degree in the equatorial Pacific. X-axis is the longitude, Y is depth. We see this warming in the equatorial thermal climate that kind of concentrated in the eastern equatorial Pacific, contributing to an El Nino-like pattern. And then in the meridional direction, again, we see a heat concentrated in the equatorial Pacific, and then they also get transported to the higher latitude. Oh, I had this written. Oh, should I just show that? Anyways. Oh, okay. So that was the TC's effect on the mean climate. I hope I convinced you that cyclones have some impact on our precipitation necessity, global heat, ocean content, and their transport. And then I'm going to highlight a part that TC's rule in ENSO characteristics. So we're more familiar with the ENSO's impact on TCs. We kind of know that we have El Nino years, we have more TC in the Western Pacific, less in the Atlantic, and in La Nina years, you can have the vice versa. But then we are thinking about, can TCs affect El Nino? So what is ENSO? ENSO is a neutrally stable, natural mode of oscillation resulting from air-sea interactions, and they are sustained by stochastic atmospheric forcing. And what determines ENSO characteristics include, first of all, the ocean state. You have your westerly wind bursts as the stochastic wind forcing, and you have carbon wave propagation and warm pool expansion that helps initiate ENSO. So tropical cyclones, as we saw before, can kind of provide all of these ingredients, right? It primes the equatorial Eastern Pacific to be warming. That affects the ocean state. You have the westerly wind bursts, we just discussed a little bit, and we have the carbon wave propagation and warm pool expansion associated with the TCs. So from this, we hypothesize that tropical cyclones may have some impact on ENSO characteristics. So we take a look at the El Nino in our model in the same simulation. So these are the Nino 3.4 time series. On the left is in the control. On the right is the TC. And just by eyeballing, you may see, okay, the El Nino magnitude may be a little stronger, but that's the first glance. And then we take a look at the seasonal cycle of Nino 3.4 standard deviation. The black is from the reanalysis, and the blue is from control. We see the CSM 1 degree model in the control has a little bit problem of capturing the seasonal cycle of ENSO. But then when you add in the TCs, the annual variation is actually more close to observations, although the magnitude amplitude is also higher. And then on the right, apologize for this very chaotic figure, but this is showing the Nino 3.4 power spectrum, and the black is again from reanalysis, and the blue is again from the control run. You can see the frequency kind of shifts a little bit to the right. It has a higher frequency in the control simulation, the 1 degree CSM. And after we add in the TCs, which is the red, we see the frequency kind of shifts back closer to observations, although your power is again overestimated. So from here, we see that when you're adding TCs in the CSM 1 degree model, it changes your ENSO annual cycle and the power spectrum. And then how about El Nino strength? So for this, the left figure is showing the equatorial SST during El Nino. And the blue lines are the control, and the red is from the TC run. And the darker the color, I believe is stronger, the El Nino event, yes. So you can see the red colors really powers with the blue, meaning that when you have an El Nino in the TC run, it's generally stronger. And then we take a look at the linear relationship between the Nino 3.4 index during El Nino and the TC PDI is power dissipation index is kind of a measure of TC wind power to see if they have any relationship. And we find this very strong relationship for, I think, medium to high intensity El Nino events. And remember that the TCs are forcefully added to the model. So this is not the modulation of TCs by ENSO. This is strictly the TC's impact on El Nino. So we find this very strong relationship between tropical cyclones and El Nino strength. And to look at the structure, we have this composite El Nino Hofmüller diagram. This is during all the El Ninos in control. This is during all the El Ninos in the TC. These are their differences. So this figure may be the most important. We see when you're adding the TCs, your El Nino is indeed, on average, gets stronger. And these gray contours are the TC wind power. The y-axis is the time series. And what I want to point out, so this is the SST. This is the ocean thermocline depth, indicate the depth of mixing. And then this is the zonal wind. And they're all consistent. What I want to point out is that we found a very interesting synergy of the annual cycle of tropical cyclones and annual cycle of El Nino. So in the early season, your tropical cyclone and their associated westerly wind bursts could trigger some eastward propagating waves that help transport heat to the eastern Pacific, kind of help initiating the ENSO development. And then right before your ENSO reaches the peak in the late fall, the tropical cyclone is kind of concentrated in the central to eastern Pacific that helps to deepen the thermocline to bring the heat up to the surface. So interesting that the synergy between these two annual cycles may have some interesting relationships that I want to dig a little bit more. So what else? Oh, okay, that's good. Worry about my time. So to summarize, what we saw is quite a lot, but we kind of designed an experiment where we want to isolate the impact of tropical cyclones in the coupled climate system using the fully coupled CSM 1 degree model. What we found is that the added tropical cyclone winds can impact our global SST pattern, leading to changes in surface heat flux and precipitation. And we find that they can increase the ocean heat content, strengthen the subtropical cells. Actually didn't show the figure, but if you're interested, and meridional ocean heat transport. We also found interesting responses in the AMOC, which I didn't think I have time to present. And then we take a look specifically at ENSO and then found the TCs can affect ENSO power and ENSO power frequency to make them more approaching the observations. And we find that TCs can indeed lead to strong to extreme El Nino events. And there is a strong positive correlation between El Nino index and TC wind power. And all these results suggest that tropical cyclones in this model setting can actively influence the climate mean state and variability, especially ENSO characteristics in this fully coupled comprehensive climate model. This has to be more dramatic. So I don't, yes. Yes, and I just want to leave some food for thought. So I've been thinking about the role within the climate system. Is it linked to the generally constant annual TC frequency? This is one question that we're asking for years. Secondly, the ocean coupling, as we see, is needed to capture small scale features in the coupled system, especially TC ocean interactions. But and in these coupled models, okay, but using coupled models, there are trade-offs because we see the SST biases in the models that can in turn affect TC activity. So there's trade-off of using or not using coupled model in our solution climate simulations, right? And thirdly, which is I think is important, is that when your tropical cyclones, even in the 1 degree model, can have climate, thinking about your TC permitting models with eddy resolving ocean and even kilometer scale high resolution simulations. And if these results, we don't know how much, we don't know if they're right or wrong. What if they're dead wrong? But then they're incorporated in their own simulated climate and how much uncertainties we're talking about in our projected future climate. And this is just one aspect to think about. Yes, and then we also sometimes when we talk about tropical cyclone simulation in future climate, we often opt to atmosphere only simulations because they have maybe more realistic SST. But then by doing that, what are we missing? So these are the questions I think may trigger some discussions here at Tropicana, especially related to high resolution climate modeling. And I would like to get your thoughts on that. And that's all. Thank you so much.
That was a really great talk, Wei. We have time for 1 or 2 quick questions.
So that was fascinating because like the ocean response, I never think about it so much. But I actually have 2 concerns. And that's, of course, going back to kilometer scale modeling. So for that beautiful animation that you showed, that was winds from a 25 kilometer CESM or CAM, right? So based on my what I've seen, I haven't done any analysis, that the wind profile of tropical cyclones in a quarter-degree model is in the way that the TC is way too large. So the wind, the ocean response is not only a function of the peak winds, but also how much area of the ocean is covered by strong winds. And this area is too large in quarter-degree models. So it could be that the ocean response is unrealistically large if you have one of those donut or truck tire tropical cyclones that are unrealistically large. That's one thing. And I think kilometer scale atmosphere model could give you a much more realistic depiction of TC in terms of size and area covered by strong winds. The other thing is this just atmosphere ocean coupling, or is there a wave model in between?
There's no wave model. Right.
I think so. When you couple the atmosphere to an ocean, you get too strong of an ocean response, because in reality, a lot of the momentum is actually going into waves that transport or distribute the momentum far away, and you get a lot of dissipation near shorelines where the waves break.
Right.
So that's one more, I guess, concern, that the ocean response could be too strong compared to reality, because you're dumping all the momentum in the ocean and you're not distributing it through waves, like surface ocean waves. I'm saying that whatever ocean response, like the cold wake, is too strong, so it gets too cold because you're dumping all the momentum right into the ocean without going through waves, like breaking waves at the surface first.
Yeah, that's a great comment. Actually, I didn't mention that in our simulation, to kind of in one way trying to compensate too strong of the wave forcing is to modify the surface drag formulation in the model. The low resolutions at 1 to 3. I don't even know for high resolution to change that, but your wind is about 25, 30. You have unrealistic strong mixing.
Right.
You have to change that to make it more realistic. So this is one way to compensate. Yeah. Thanks for the great comment. And I think for your first comment about the 25 kilometer tropical cyclone being too large, that's also a very valid concern. I think one thing is that when you use a coupled model, even though you're using the kilometer atmosphere forcing, and when you're coupling with the ocean, everything has to be calculated onto a common grid. Normally, it's down on the ocean grid, So it will still be kind of diffused to be large and then everything, right? So it's hard to constrain these kind of, this aspect of the bias. And also this study is actually more focused on the modeling world rather than the reality, right? We want to know what happens in the model, right? So yeah, those are, if we're thinking about the real world, those are all the uncertainties there.
Thank you.
Yeah. Right. Yes, Susanna has a paper on that.
Okay, we'll take a few more questions as our projector wakes back up. By the way, for the record, this says to avoid injury, do not throw at people's heads.
Awesome. Yeah, I'm really impressed by the modeling work you did. I mean, that must have taken so much time and determination. So it seems like you know CESM really well now. And so my question is more about parametrization. So imagine there's a perfect world in which we run pretty high resolution couple simulations and those describe the effect of TCs well. And now we back to a coarser model because we're trying to make it accessible. So which parametrizations would you target to represent what you found? So is it all in the RC flux parameterization? Does it also goes into some momentum parameterization? So I don't know the parameterization in the ocean as well, so I'm curious.
Right. I think maybe the vertical mixing scheme.
Okay.
Yeah, especially when you go to eddy resolving timescale, the mesoscale mixing scheme and the vertical mixing scheme, they all have to be scale aware, right? But right now, when you're going to a coarser resolution, you have to do a different scheme at different resolution. So that's something that I think should be part of the parameter consideration that you mentioned.
And then, oh, sorry, go ahead.
Yeah, but I'm only thinking about the ocean. I don't know if you have.
No, I mean, two quick follow-up is like, how would you know when there's a TC then in the parameterization when you're at a coarser scale? And then I'm also curious about the cat.
I wouldn't know because I don't think, yeah.
That maybe there should have been a TC, etc.
There should have been a TC.
From the ocean perspective, the ocean parameterization perspective.
You think which parameter should tell me there should be? I think it.
Well, we can talk more.
Oh, sorry. Yeah. But the cat, I found on Etsy is like a store that sells croissant cat for your croissant hat for your cat. The store is in Canada. I'm getting one when I get home.
All right, Hui, thank you so much. One more time, I know there's a lot of follow-up questions. I still see quite a few hands, so you've sparked a lot of discussion, but we do need to move on to our next talk. Let's thank Hui one more time. Our next talk is by Pradeebane. Okay, we're good. We're good. It's because you need me chair. That's what happens.
So good morning to everyone. I am Pradeebane. I'm currently in postdoc at the LSCE within the Cyclone project. I'm going to present you a study I'm currently doing with Stella Bourdin and also Mathieu Vrac and Davide from the same lab where I am. So it's about random forest-based tropical cyclone detection. So I just start with a few words of context. So we know that the tropical cyclone are quite well documented during their lifespan, but we have still some problem to actually resolve the processes governing them in the GCM, so cross resolution models. And there are some many uh, uh, studies working on the simulated tropical cyclones within the models, and they are using some detection schemes, deterministic detection schemes that are usually subject to the model resolution, and also sometimes need many numerous variables that are not always available in every model output. So here is the idea is to detect the atmospheric situations that are actually related to cyclone within these climate data sets, and from a relatively limited number of variables. So here I will use this approach called random forest. I will take a probabilistic version of it. So I'm going to show what I've done so far. First, First, I've started to do the work on the tropical Atlantic. So here I've filtered every observational data from the IBTrax data set. I took only every situation, tropical cyclone situation that reached, this tropical storm intensity. And I choose that the low resolution data set, I choose low resolution variables from ERA5 dataset, I took the mean sea level pressure, the rotation, so relative vorticity at 800 hectopascal, the geopotential thickness between 300 and 500 hectopascal, the total column vagal vapor, and the width speed. So basically, it's is it possible to use this screen instead? No. Okay. So basically, it's the physical characteristics of the cyclone, the outflow, the shape, the intensity, and the position in space. Okay. So not so much, but okay. But okay. So how I said that I select tropical storm intensity based on the mean sea level pressure and the 10-meter wind. To take that into account, I just divided the region into 10 by 20 degrees windows, overlapping windows. And instead of taking the whole data within the window, I just summarize it in mean, standard deviation, minimum, and maximum. I use also a cross-validation setup. So here I just divided my period into six-fold cross-validation process here. I have 42 years of cyclones. I use each time 35 years for calibration and 7 years for validation. So I took 7 years. I leave out 7 years. So for the first set, it's 18. So it's spaced every 7 years, and I just shift of 1 year for the other. So I have 6 test sets. So I do all the analysis on the reconstruction, cyclone reconstruction over these test sets. So to overcome this unbalanced data, so basically the ratio within IB tracks is 1 for 99. Sorry, there's 98% of the situation that are not cyclonic, and only 2% that is actually cyclone. So in order to balance that a bit, I just undersample the 0. I took ratios of 25 to 1 to do calibration. I'll talk a bit later why I choose that. And there is many ways to do this undersampling. So I just do 100 random forest to with 100 ways to choose randomly this undersampling of zeros. Sorry. And how I construction is based on the average probability I got from the 100 random forest. And so, sorry. And how I define it's a cyclone is just if I am above 0.5 of probability, I say it's a cyclone for now. Maybe we can choose a different threshold for that. So a bit from the result I get from there. Here is the graph about the factor of importance. So what is that? Is it shows the contribution of each predictors I put in the random forest that decrease the impurity of your sample. This random forest is on this impurity concept, which means that the whole data set has the maximum impurity, and when you grow your tree, you decrease your impurity to the maximum you can from the random forest. And here, because you have the contribution of each one of them that decreasing this impurity in when you grow the tree. So what's interesting is that if you take the top like 6 variables, you have the standard deviation of the relative vorticity, the maximum wind, the minimum SLP, the maximum relative vorticity, and the total column water vapor maximum. So basically, it's quite sensible in terms of physics. You get the variables that are actually can explain why you have a cyclone or not. And the others are quite lower. So it's maybe if you just limit the analysis with the 6 top variables, it could be enough to have it's here. So yeah. So if the random forest gives me 1, so maybe if there is a cyclone, the location is given by taking the position of the minimum SLP within the 1 box. So I can determine just like that simply where is the cyclone in the data set. For then I have to count the tracks. So first I have the hits, so which are observed and detected by random forest. The missed one are those which are observed but not detected, and the false alarm are those which are not observed but detected by the random forest. And I just compute 2 simple rates: the probability of detection, so which is this fraction, and the false alarm rate. And the better you have a higher probability of detection and a lower alarm rate. And for the analysis, I limited. So I just filter every tracks that are equal or above 24-hour length. So I have So for the test sets, I have a false alarm rate of below 8% and about 78% of probability of detection, so which is quite good compared to the deterministic scheme that exists. And if I just do the work over a whole data set, so I perform a calibration without test data set, I have 2.3 false alarm rate and about 94% of probability of detection. Sorry. So if you remember, I had the 4 tracks that are so there is a hole in this track because I filtered above a certain level of pressure and below a certain level of pressure and above a certain level of wind. So in the observation, actually, I've filtered the positions here, the track here, part of track here. So we are able to actually separate these 4 tracks and reconstruction. So the observations are in orange, and the reconstruction are in blue, and the observation are orange. We have very different types of tracks that are quite well captured here. And I also, so it's an histogram of the track durations. So it are the duration in the observation in IB tracks. So, and what I've reconstructed, the hits are in blue, and green and red are the false, the missed one and the false. So if you take the blue, you can see that the shorter, actually, that the shorter tracks are, we have more difficult to reconstruct the short tracks, which are the usually the less weaker cyclones, and so more difficult to reconstruct, and maybe not even in era 5. Sometimes you don't see those tracks in era 5 so as well. So yeah, to explain, so I'm not sure you can see anything on that, but here are the tracks, that the missed ones on the left and the false alarm on the right. And there, the color represent on the top the probability determined by the random forest. The second line is the minimum pressure in era 5 and the maximum wind in era 5 on the bottom. So for the miss tracks on the left, you can see that most of the probabilities are below 0.5, except one track here, which is red, so about 1 of T. So this is a particular case where you had another track which is stronger, very close to that one. So I was not able to actually separate them properly here. And you can see that the wind is also quite strong, and the minimum pressure is below about 980 hectopascal. So it's actual really a cyclone, but it was the difficulty I had here. And on the right, for the false alarm, so if you look at the probabilities here on top, it's something which is close to the edge of the domain. So there is a border effect, I guess, or something which is quite random here. And if you just look at most of the probabilities are very close to 0.5 here, except those here, the ones here. So if just you increase the threshold to 0.6, you probably will remove those false alarms. So these are false alarms, but not well. I don't know how to qualify them. It's not that dangerous. I don't know. Okay. So yeah, about the random forest bias for unbalanced data, we know that is actually a basic classification. That's it. And if you have here you have too many zeros, so the random forest will be better in. So you have somehow to undersample the zeros, and here you have the POD for different balance here. So 15 to 1, 20 to 1, 25, etc. And you see that if you increase, sorry, the ratio of zeros, the probability of detection decreases, but the false alarm also decreases. So you have to, I took 25 because it was somewhere in the middle of that. And so the idea also is to use that random forest to detect cyclones in the models. This would be the next step. So here I just tried to see how generalizable, scalable it is to another basin. So basically I took the random forest calibrated over the whole data set, this time over the Atlantic, and that I just used that over East Tropical Pacific without any knowledge about the cyclone within this region in the calibration of the random forest. And what we got is quite good, actually. Maybe we can work a bit on the fourth arm, but we are about 16 without any knowledge of cyclones over these regions. And we have a probability of detection of about say 76%. So I think it's quite promising for the future and also for evaluating the cyclones in the Mars. So you have just two examples of cyclones, Eastern Pacific cyclones. Who you want for that? I don't know. So there is still some work going on and future work. So the idea also is here to convert this approach to the deterministic approaches. So it's a work done by Stellar currently. The idea would be also to produce some risk maps, something we have a probability of cyclones for different locations. So I hope to be able to reconstruct, at least for the landfall, some probability maps to of occurrence of cyclones. Could be interesting to have such maps. So the next step also, as I said, would be to use that for climate models, for especially high-res MIP simulations. And there are two issues we have to work on. Is maybe there would be need for bias correction. I don't know if I can directly transfer, it's directly transferable to models. If there are huge discrepancies between ERA5 and the models, I don't know if, what the capability of this approach. And the other thing is the climate projections. If you have completely different range of variable in the future to compare to ERA5 right now, so it's a stationarity problem. I don't know how it will react. So there's maybe some other things to add into this random forest to be able to use it for models. I think that is for me.
Thank you. Thank you for the talk. Did you try to play with the threshold of 16 meters per second to see if you have less missed tropical cyclones? Because we know ERA5 is underestimating the winds. So you may have the problem to decrease the mists and to increase the false alarm, but did you try this?
No, but I can just put a threshold on removing the tracks that are not actually cyclones, just tropical storms. I haven't done that, but I can try if I am able to drastically reduce the false alarms in that process. Thank you.
Yeah, thank you. Very nice talk. I had a similar question to that, but I'll ask this other question as far as the computational performance of using something like a random forest. So, I mean, obviously the training you kind of have to do once, but if, for example, you wanted to run this on a different reanalysis or on high-res MIP, what is how much effort is it to run it? Does it run relatively quickly? Do I have high memory requirements?
Yeah, what is a bit long is the pre-processing of the data. So just basically extract the data over the area you need, and compute the statistic over each box. So, and once it's done, it's very fast actually.
Thank you.
It's a few minutes maximum for 100 random parts. I mean.
Great. And I had one more quick question on the sneaking. I was really a little bit perplexed when you showed the permutation future importance type plot or the variable importance.
Yep.
there were some that said standard deviation and then mean, but
Yeah.
I was really confused by,
Sorry, yeah, I haven't told, yeah, this one you mean?
yeah,
Yeah.
like why do you have mean of something if it's one sample, I would think?
Because I've performed that 100 times with different sampling of, I've done a 20:1 ratio sampling, undersampling of the zeros, and I've performed that 100 times to see if there is an effect on taking different sets of zeros over the results. Oh, sorry.
Yeah,
Yeah, here. Yeah, okay. I completely missed the question. Sorry. Why I have that is here actually. If you just cut the area into different boxes, and instead of considering the data over the whole region, I just summarize it for each box. I take the mean, the standard deviation, and the minimum maximum for each one of the 16 boxes. Yeah. So I don't have so it's 3020 grid box area. So for each one of these boxes, so instead of all that, I just have 4 variables for synthesis.
Huh, okay. I don't fully understand, but I'll pick up the discussion later. Let's thank our speaker one more time. Susanna, any other? No?